talk on this session. And this is by Professor So-gu Kim from the Korean Seismological Institute and his co-authors.
Good morning, everyone. Today I'd like to talk about nuclear explosion of North Korea using regional and teleseismic arrays. As you know, there's some strong controversial concern over source depth of North Korean nuclear tests. Some experts, especially some American experts, keep insisting that North Korean nuclear tests would detonate at a shallow depth from 200 to 600 meters based on the satellite and the SIR image interpretation and including scale depth as well. But I'm afraid that they may not be correct. North Korea tried to feign that everything on the surface, such as spoil piles, infrared tunnels, or some disturbance, anything, is a kind of something like looks like the real location, but that's not true. Our paper was not accepted by some geophysical journals because of the overvariate determination. Some reviewers keep saying that our overvariate determination is not correct. It's a kind of a fanciful conjecture trying to justify our findings, but that's not true. I'm pretty sure that our overvariate determination is correct. We used, based on the pure seismological concept, using depth space readings, using all different kinds of seismic data, even considering the pre-existing mining tunnels near at the test site as well. I think this, we did not use the ostensible satellite data. We did not use any scale depth, which is based on the relationship between depth and seismic yield, cannot be applied for North Korean nuclear tests because North Korea did not care about the cost and manpower. And so I'm pretty sure that our pure seismological concept, our determination may be correct. And I think this problem is very sensitive in terms of political problems in these days. And but in conclusion, the possibility of the overvariate determination may affect MB to MS as well as the seismic yield, and maybe including the preemptive strike as well. I'll explain more detail in the next slide. Okay. This is a global and local seismic network which we used in this study. I'll just go a bit faster. And this location, the depths for 5 North Korean nuclear tests, as you see, they're widely disputed by different organizations and researchers. Like IDC, there are red ones, and the yellow one is USGS, NEIC, and there's some other research guys like Murphy and J.W. Chang and Wen and Israelson, something like this. They're all widely distributed. And the IDC is much more reliable than the NEIC because they get together, as you see. And here 2006 has some problem because everywhere has a different location. And this is just a list of the 5 nuclear tests of North Korean nuclear tests. Everything is done by USGS except the depths. Depths is done by our studies. Our depths are already greater than 2 kilometers. This is skip. And the method we used body wave, spectral nulls, or body waves as well as soft waves. Now it's a body wave from teleseismic waves. As you see, they're all spectral nulls. They use the trace because we we take average spectra and then spectral null right here. As you see, they're more or less. So the spectral nulls that cross about 1.25 and 1.26, 7, something like this. They are very much identical. This 2006 January anyway. Next one is 5 nuclear tests using by WRA. And as you see, the 2006 and up to 2016 September. There, or you can see the spectral nulls. Sometimes we use the long range of frequency range, so you can compare what happened there. There are some multiples, and the other side is a YKA. This YKA station. This is also the local near-field seismic arrays in KSRS in Republic of Korea. 5 arrays here, 2006 and 2000, something like this, is up to 2013. And then 2016 September, they have 2 spectral nulls. One is sub-sPn plus Pn, and next one is sPn plus Pn. They have different the spectral nulls you can see. Okay, this is another one. USRK in Russia is also spectral. We didn't take 2006 because 2006 was not detected. And you can, here is strange anyway. We have only spectral nulls sub-Pn plus Pn. Now, we try to make some kind of stacking, common depth point stacks. It's a kind of a beamforming anyway. So one side, this side is KSRS here. This is one 2006 January events. And we can see very much the first order P wave there already the same time here. And we can determine even the depths, sub-Pn plus Pn, something like this. Here is sub-P plus minus Pn. Okay, we can get the spectral nulls from those common depth point stacks. As you see, here's a KSRS, this one here, 1.75 hertz, and then the 2006 is a 1.26 hertz. Is a more, the slow, low frequency. That means it's deeper than other tests. And then here, this side, here is a teleseismic array. Is a 2016 event, and they are very much identical. 1.25 hertz here. Can go faster. This is just a list from the spectral nulls. We can calculate depths around 2.15 kilometers here. And this is another one we calculate from the near field. 2006-2009 is 2016 January using the KSRS. Also, we can calculate depths here around 2 point something like it, greater than 2 kilometers here. And okay, now this is synthetic seismograms for near field and far field. I can figure out, we can compare with the observation with the synthetics, and they're very much identical. You can see here is a sub-Pn plus Pn. These are synthetic spectral nulls at 1.75 hertz near field and 1.25 hertz on far field. Assume that the depth is 2.5 kilometers. So you can find here, you can find it right here, near field, far field. This is anyway, this is soft waves. We try to figure out what happened for Rayleigh wave. In this case, it's the RG wave, spectral nulls. And this data is from Dongbei. This is temporal seismic network, Dongbei data. And this is 2006, 2009. We can have a spectral here. 0.134 hertz. Indicates that the depth is around 2 kilometers. We can take it in just as you know, the spectral nulls with normally the spectral nulls of the rail wave. It depends on the mechanism depths. Then rather than the medium and the source size. So we see here spectral nulls 0.134 hertz. Here only 2006. The rest of them, they don't have any spectral nulls. That means 2006 has a different source mechanism. We assume that will be many people studied that the 2006 event is a kind of a shale-based source which generates algae waves. So this mechanism is maybe a 45-degree deep sleep. So another study, USRK also, we found 2016, September, have a spectral nulls here. This is, I think it's due to also the mechanism, also is some azimuths from the different location here, the USRK. This is just forward modeling using the known strike, deep, and rake. We try to find those spectrums. And 2006, in case there's a 30-degree and azimuth and 48, about 45 degrees deep sleep, and the rake is 90, is deep sleep, 45-degree deep sleep. And in this case, we have a spectral nulls here. This is 2006. Rest of the different mechanism, we cannot find any spectral nulls. So we just studied for soft waves. And this is some examples whether or not our method can be used. For earthquakes, this is Gyeongju Earthquake in Korea, South Korea. And one is detected by WRA, and the other one is KSRS. The depth is 10 kilometers was determined by many other ways, even USGS and some MT solution and other ways. And here we can, as you see, the depth is about here. So the near field, here this is far field, WRA, Warramunga, Australia. You can have it here 10 kilometers here. KSRS here, we have also the spectrum here. This is multiple even there. One here, is here 9.5 kilometers. It's very close to the depth with the other method. This is another people that studied the Fox and others, and they studied some, try to figure out the depths using the spectrum nulls of a rail wave. And they found it here is about 22 kilometers. And the spectrum was 0.0254 hertz. This paper was published in the Geophysical Journal International. This is particle motion of soft waves, and we can compare with 2006 and other tests 2009, 2013. And 2006 is a different particle motion here, and compare with the 2009, 2013 test. That means that the 2006, this first nuclear test has a different mechanism. Now, this geological map and the satellite image. This satellite is a French satellite, by the way. It was produced 2000, I think 2009, something May 14. That means just right before second test. As you see, this is a geological map. The other side is satellite image. And there are already 3 portals. This is before second test. It indicates that there was a portals before. Means something like they use this tunnel entrance for other things like mining exploration. I'll show next slide. Okay, this map is produced in a geological book in North Korea, as with this cooperation with Russia and the DPRK. And here, as you see, this is a mineral deposit and the structural geology near this nuclear test. You can see the red one here. This one is, there are a lot of mineral deposits right here. But at that time, I didn't think they developed, they explored the minerals. Maybe during this was in 1964, so it was developed a long time ago already. And then here this molybdenum, MO here, red one here, molybdenum mineral here. This is related to the tunnels.
Professor Kim, we have 1 more minute allocated to you.
This is my sketch, the tunnels, how it looks like. And you have some inclined here, one portal right here, for example, and then there's some inclined tunnels right here, and then some horizontal tunnels, and right here is some bottom line here, the horizontal tunnels, and there's some explosion source right here. And why I show this map, and I show next slide, here this one. This is real mining map in Korea, South Korea, is a Sangdong Mine. This depth about 1,573 meters. And then here, there are a lot of the horizontal tunnels. That is, we call the levels. And each level is, there are about 4 levels. It is 20 meter, each 20 meter. So up to here, for example, the 1,000 meter here. And the bottom here is 200 meters. So many levels. This is the ventilating shaft. Here's some inclined shaft, here's a vertical shaft, everything like this. So what I mean is a tunneling. Is what they only excavate the tunnel in. Is a tunnel is excavated for nuclear test as well as some mining.
So, Professor Kim, we thank you for your contribution. In order to be fair for the other speakers, we must ask you to bring this to a close, and we can have some further discussion after the first 3 talks.
Okay.
Thank you very much.
The next speaker is Aurélie Guillaume from France, from the CEA in France.
Okay, thank you. So to start, so I'm working at CEA in France, and so for everybody, CEA is a French alternative energy and atomic energy commission, and it functions as a national data center in France. And so some of our missions are to fight against terrorism and nuclear proliferation. And so in that way, we contribute to the International Atomic Energy Agency and to the CTBTO. And part of this work is done through a continuous monitoring, seismic monitoring. And so thanks to this monitoring, we were able to detect all 5 declared nuclear tests in North Korea on the Pyongyang site. And so this timeline shows the 5 tests. The first one started in October 2006 with a magnitude MB 3.8, and the last year was a busy year with 2 events, one in January and one in September. This figure shows the waveforms, the vertical component waveforms recorded at station MDJ in China. This is the closest regional station at 370 kilometers away from the Pyongyari site. And what you see from the top, you have the first event in 2006. At the bottom one, you have the last one in September 2016. And you see that all the waveforms are very similar and at this regional distance. And so the only difference you can barely see are in the amplitude. So you have differences in the amplitude. And so this first observation that can be done within the first minutes following the 5 explosions indicates that those events should be of similar types and similar location. So bottom plots show all the same waveforms but overlying each other. And you see that you have a strong P wave energy and some weak S and surface wave energies. So that gives us another information that those sources are not typical of tectonic events like earthquakes, but would have some information for anthropogenic sources with isotropic component. One of the first approach that we use at CEA is to use the MB-MS difference, MS being the surface wave magnitude calculated around 20-second period, and MB is the body wave magnitude calculated around 1 Hertz. And so it has been shown that we can separate a population of earthquakes from population of explosions by just using this criteria. For explosions, MB tends to be larger than MS. At CEA, we'll prefer to use an extended version of the MB-MS approach by using MSVmax, which allows us to use a wider period bands for the calculation of MS, not just the 20-second period, but something between 8 and 40 seconds. So we do 17 different frequency bands at which we measure the amplitude, and we get a MS value. So MSVmax is a frequency-dependent MS magnitude. And so the advantages of using this approach is that it allows us to use a broader range of frequency band at which we can measure the MS. So it's not restricted to the 20-second period. We can also have an extension of the distance range at which we can make the measurements using both short period and broadband stations. And this can be applied on both Rayleigh and love waves. And by doing that, we have a tendency of having more MB-MS pairs of events, so that gives us more discrimination. This is what we get for North Korea, for the 5 events. On the right, you have the value of MSVmax Rayleigh wave, on love waves, and on the left, Rayleigh waves. The orange line is the discrimination line proposed by Bonner et al. In 2006, so prior any of the DPRK events. And you see that when we use this criteria, we are basically failing the discrimination of the DPRK events. Again, that's an empirical line. It should be revised, and the IDC already has a revised version to try to separate the nuclear test of North Korea and to put them underneath the line. Another approach would be to try to consider both Rayleigh and love waves. And here I'm showing on the y-axis the MSVmax calculated on love waves, and on the x-axis on the Rayleigh waves. It has been shown previously by Bonner et al. In 2012 and by ourselves at the last Science and Technology meeting in 2015 that when we consider typical events in Europe and in Italy, so mostly tectonic events, 80% of them lie above the 1-to-1 line. So would have larger MSVmax loves than MSVmax Rayleigh waves. And if we look at the DPRK events, you see the opposite. That's excepted for the 2006 event, for which we have a low signal-to-noise ratio and so some spurious measurement. We have all the other events that are either on this line or below the line, so different from tectonic events in Europe. Now, if we look at the MSVmax value recorded at regional stations, you have here on the top the Rayleigh wave, and on the bottom the love waves, and you have different patterns. What we see is not what we would expect for an explosion. There is no isotropic pattern of the MSVmax value. You don't see an homogenization of the value around North Korea. For Rayleigh waves, you tend to see larger Rayleigh wave MSVmax on continent compared to the oceanic path. And that's the opposite for the love waves. The love wave MSV max tends to be lower on continent. Now, if we try to compare events per event, we usually see there is similar patterns, except between the January 2016 and the 2013 event. The 2013 event has larger love waves, and that's what we see here on the top right. You see that basically all the stations are in blue. That tends to indicate that the MSV max love wave calculated for the 2013 at the same station as those that have been used for calculation of the MSV max love wave for the 2016 event are larger. And that's the opposite when we look at the Rayleigh wave. So there is really something a bit different about the 2013 event. And the 2013 event seems to be enriched in love waves compared to the other events. I move on to the second part of this presentation, which is the moment tensor inversion. So to try to compare all the 4 largest DPRK events together, I performed the moment tensor inversion using the identical parameters that would help for the source comparison. So I'm using 8 regional stations that are distributed around the source. So you see them here with the red triangles. I'm using 3 velocity models. 2 are from Ford et al. 2009, and 1 from CRUS-2. It's for station Majo in Japan, and it's to accommodate the oceanic propagation. I'm using waveforms filtered between 15 and 30 seconds period, and I fix the depth for all events at 1 kilometer. I'm showing here the results. So for the 4 events, you see the waveforms in black for the data and in red for the synthetics. And you see basically that you have a very good fit for all 4 events. The fit is of good quality. We have more than 70% variance reduction for the events of 2009 and 2013. And even more, we have more than 80% for the 2 events of 2016 by using the same 8 stations and the same parameters. The station distribution, as you can see, around the beach ball is good. We are covering the focal sphere. In terms of the decomposition, we see that the sources are mainly isotropic with explosive component. It's about 63% for all events. The second part of the source is CLVD, about 30%. And we have a very tiny double couple component for all events. It's only 3% for 2009 and the 2 events of 2016, and we have the double for 2013, only 6%. It's another view of looking at the source decomposition for all 4 events. And you see here the large explosive component and the very tiny double couple component. We tested our solutions by doing jackknife tests. We basically tried to see what was the station stability in the solution. So we removed 1 station, 2 stations, and 3 stations out of the 8 optimal stations. And that's what you see here. Basically, we have a stable mechanism, we have a stable moment magnitude as well, and the fit doesn't change much. The colors indicate the isotropic component for all those solutions. And as you see, that's mostly green, and it's about 64%. That's an example for the January 2016 event, but we do the same for all the other 3 events, and that's similar. We perform a network sensitivity solution for all 4 events by calculating 400 million random moment tensor solutions, and those moment tensor solutions are tested against the observed data. And this is what you get. You are far away from the center part of this plot, near the double couple region, where you would expect tectonic earthquakes, but not explosions. We are not at the top of the plot, again, for all 4 events. We are not near the explosions. It's because we need to accommodate for this tangential energy we record for all 4 events at these 8 stations. But we are close to the explosion and close to the opening crack. Just to show you that I didn't try to make the results fit whatever I wanted to show for the 4 DPRK events, here I'm showing the results for the magnitude 5.3 South Korea earthquake sequence that occurred only a few days after the September 2016 event. This magnitude 5.3 was the largest instrumented earthquake in South Korea. And you can see on the top here a comparison between the waveforms recorded at station MDJ for the North Korea test and at station INCN for the magnitude 5.3 earthquake. And they look very different. The moment tensor solution here also use 15 to 30 second period waveforms. And it's calculated in red for the main shock. The green one is the foreshock, and the blue one is the largest aftershocks. And for all 3 events of the sequence, we get dominant double couple component and very small isotropic components. And the network sensitivity solution also shows that the earthquakes of this sequence are mostly with the deviatoric solutions and do not fit on explosions. So to conclude, what I'm showing is that the 4 largest events have very similar waveforms, of very similar locations, and in terms of moment tensor solutions, they are also very similar. So the similarity between the moment tensor is in agreement with a similar waveform location and waveform look. We have a very small double couple component for all 4 events, but we have a slightly more percentage of the double couple component for the 2013, which shows the largest tangential energies, the largest low waves. Finally, I want to show this one, that the double couple component we observed seems to be in agreement with the regional stress field that has been published for the region, according to paper Jin and Park 2007. We can also mention that the second major part of the solution is the CLVD component. And a slight deviation of the CLVD component could also affect the amplitude of the low waves. I'm not showing it here too, but there probably have been talk or there will be posters showing some potential effects of the topography, as the 4 tests occurred on a mountain, but not necessarily at the same depths, and underneath the same point of the mountain. So topography effect could also have some influence on the generation of the low waves. Thank you.
Thank you very much. We'll go to the next talk now, and if you have any questions for Ms. Guillaume, please do so during the discussion time. The next talk is by Professor Kim from the Lamont Doherty Observatory of Columbia University.
Good afternoon. I'm Won-Young Kim. I'm glad to talk about small seismic events around North Korean nuclear test site. Not the major nuclear test, but the small seismic events. Together with my colleagues Eun-Young Cho, Yong-Gyu Liu, and at Korea Meteorological Administration, and John Ambrose at Lamont Doherty. So the major talk is about the small seismic event, and I'll show you 2 examples of the small event on May 12, 2010, about magnitude 1.5, and then the latest one is about magnitude 1.8 to up to magnitude 2 in September 11, 2016, just last year. And I will emphasize that showing some newly available local or near regional data and use of that inevitably for small earthquakes and seismic events around test site. So in this case, I would like to mention about Dongbei Seismic Network, about 16 station deployment between 2004 and 2010 by Dr. Kinip Chun of Canada, who now retired and who has kindly made data available. And one of my colleagues, Professor Paul Richards, sitting here, he actually went to his house in Victoria Island in Canada with a suitcase and brought the data 2 months ago. So we are starting to pull them out and starting to use. And then I'll show you some stations in South Korea, near the Korea, South and North Korea border. They're starting to put some borehole seismometers, and some of them looks like quite quiet and relevant for this kind of research. So mostly when we were doing nuclear testbed monitoring related research, obviously the key words are the detections, location, and identification. So today I'll talk about briefly on detections and identification, and especially in CTBT monitoring regime, it's obviously we are talking very small seismic event. So here map shows the North Korean test site and surrounding regions, and these are Dongbei network stations, total of 16, and then these are stations in Korea, South and North Korea boundary, which now, the red ones, total of now 37, became a borehole installation. And of course, there are MDJ of GSN and 2 array, IMS arrays, USRISK and KSRS down here. So area is fairly well instrumented, though for small earthquakes and seismic event, it still is not enough. On general, we were doing some various ways to detect signals. I'm usually doing very much on visual inspection, but obviously you cannot do too many data points. So the next one we are using was the sort of traditional short-term, long-term average detector, which you can process vast data set, but that is not very accurate for small size earthquakes if there's a large noise, background noise. So obviously for the array installations, one use array processing and beamforming to enhance that, but recently we've been able to use waveform cross-correlation detection, which then lower the magnitude range. In this area, probably about magnitude down to 1.5 can be now detected by using waveform cross-correlation. Today I'll show you another technique that we are using that is called envelope template detector, which simply speaking is the same as waveform cross-correlation, but it's simpler form and it's faster by an order of magnitude. So here, these are a traditional waveform cross-correlation detector for 2 nuclear tests from North Korea in 2009 and 2006. And these are corresponding envelope, just basically calculating RMS amplitude for each second window and plotting continuously with about 0.1 second offset. So the sample rate is dramatically reduced. So when we apply that detector for 6 months of the data by using 3 station pairs, here's number 4, 6, 9, and using 3 envelope detector, using a 2006 nuclear test as a template, we run about 6 months of 2009, and we detect about 3 or 4 events. Obviously, the larger one is 2009 nuclear test you can easily detect, but then there are 3 or 4 small ones, and it turns out that we couldn't detect the local small earthquake, but these are the deep focus earthquake from the other side, which has almost a similar behavior in terms of waveforms and slowness of arrivals. So we were able to run so far 2 templates using the whole six years of data. And so far, we didn't yet found a convincing small event. Perhaps we have to now use more templates by looking at either autocorrelation or just STLTA detector to see if there's any hidden event that we can use as a new envelope template. I'm changing to another issue of the identification, and obviously in this area, these red ones are earthquakes that so far we've been able to identify it, but most of seismicity is around south of Pyongyang in North Korea. So in case of identification, we are using signal types, P wave, S wave, or surface wave, or you can use vertical component, horizontal component, or 3 components together. Of course, when the frequency is high frequency or low frequency, depending upon where signals are most obviously different. So here the example is 2016, last September event, recorded at nearby station, 5 nearby stations. First one and last one is 2 short period stations in Korean Peninsula, in the KMA station, near the border, near the coastline. Red ones are the ball seismometer, and these are MDJ Mudanjang station. So from these plots, these are the horizontal axes are the group velocity axis. So you can see these stations shows about 3.5 the LG wave type of signal, and these stations shows about 4 kilometers per second. That's about between crustal wave and SN type of mantle wave. I can show you briefly what's the difference. And then in the other 2 arrays, the USRK and KSRS, which was used by Bobrov, Kitov, and I forgot the name, Misha Rozkov, these 3 reported last year. So we look at the data, and here you can see in naked eyes some of the energies at the arrival time. So these 2 signals and these 2 group differences are that signal coming through these paths, straddling through the oceanic crust. These are the bathymetry. Obviously, this part is oceanic crust, and the stations to the little bit inside here has very little effect, but side coastline, they're affected by that, so these are blocked forwardly, and they arrive a little bit early. This is a case of 2010, May 2010, a small seismic event, comparing with 3 components at Dongbei Network Station number 8. And these are 2006 nuclear tests, 2009, and this 2010 sort of questionable event. You can see that P wave arrivals are aligned, so obviously they are all coming from the same area. And then the shear wave here, the slight difference. This guy, the last one, has a little more shear wave than the other ones, the other 2 nuclear tests. Here the P waves are a little bit stronger on the nuclear test side, test event. So you can have some idea that it might be slightly different. Now, in order to identify these events, we are forming a base frame which consists of events, sort of sample data. This is one of the most difficult jobs, to see what events are the really confirmed earthquake and what are the explosions. And then, based upon these data, we can form a rule. So these are an example, one of the best example, 3 trace, 3 components of the nuclear test in 2006, and an earthquake nearby, but the same distance, almost the same distance, 180 kilometers apart. These are nuclear tests, obviously. These are earthquakes. There are some effects due to paths, but you can obviously see very different. So we are using basically this difference, that earthquake will have strong shear wave, while the explosions have strong P wave. So when we set up some sort of a dozen earthquakes here, circles, and explosions, plotted together on a frequency, discrete frequency, and a spectral ratio, you can see two groups are obviously separated out. This is not just to sort of cherry picking, it's to try to get best examples representing the whole area. So these two groups are identified, and then we try to see where we can maximize the difference. Okay? So for example, these red ones are 2016, the last fall event, small earthquake. We plotted here. Obviously, they belong to red ones, red square here, belong to earthquake population. And then 2010 event, now here the blue ones. Around here, they follow the earthquakes, and around here it's a little bit higher. But that is probably, I believe this is around where the signal to noise ratio getting small, weak at high frequency. So in this case, we set about between 6 to 10, about 6 to 12 hertz. This will be the best frequency band to identify different type of source. So once we apply those rules, then we find just a simple linear discriminant function. The details are important, but once we find these rules and input these equations, simple equation, each frequency, in this case 6, 7, 8, 9 hertz amplitude ratios, then you will be able to get sort of D we use as a discriminant score. And so by using the rules, we isolate them. And these two are 2006 and 2009 nuclear tests. This event is 2016. Obviously, it falls into earthquake, and these green ones is the 2010 event. So these are way we are trying to identify small seismic events, whether they belong to this group or that group, but always there is no 100% certainty. So in this way, we were able to put some sort of a statistical touch that about 0.6% misclassification probability. So almost we are certain that these two belong to earthquake population. Okay, thank you.
Thank you very much, Dr. Kim. We have time now for a discussion and for any questions you may have for the three speakers who presented their work in this session. So, are there any questions from the audience? Okay.
So, if I may begin first with a question to Professor Kim So-gu. We have had three very different presentations in the last 45 minutes. In your presentation, you are making an estimate of the depth of the event from your best measurement of some interference between the main P wave and the surface reflection. My question to you is, what do we know about the success of this method in application to nuclear explosions in the past for which the actual depth was well known? I must apologize for asking you to abbreviate your talk, but I here give you an opportunity to expand upon your main idea.
Yeah, that's a good question anyway. Nobody knows the actual depth of North Korean nuclear tests. That's why everybody has a different guess. First of all, most people think about the satellite image and also SIR image interpretation, and then including the theoretical model scale depth. Three factors they're using for estimates the source depth of North Korean nuclear tests. And they neglect actual seismological method I don't know why, but the long time ago, they used this method to determine the source. You know that the depth already. Because,
but may I say that in the past application of this method, it did not always work very well, because the measure from the seismogram of the time difference between the main P wave and the surface reflection in practice was longer than you would expect from the known depth of the explosion.
That's correct. If you're longer, like earthquakes, it's easy to determine you can use a phase interference, distracted interference using the phase difference. First arrival P and then reflected sub PP. It's easy if you have for earthquakes. But explosion normally less than 3 kilometers. It's very shallow. But so far, most of the nuclear explosions, they all know because they really don't care about, I don't know what the expression is good or not. They don't consider the kind of in secret, safe. But as far as I know, DPRK North Korea, the most important thing is just safe and it's secret. That's why.
Thanks very much, Dr. Kim. Are there any other questions either for Dr. Kim or for the other speakers for the 2 previous talks in the session for Ms. Guillem or Wei-Jung Kim from Lamont Doherty? Yeah, one. Can we have a microphone, please, over there?
Yeah, well, thank you. One question for Professor Kim.
Yeah.
I don't know, the source characteristics, would you have an idea whether it's due to reactivation of existing faults or generation of new faults?
I didn't hear it. What
The source characteristics.
source characteristic.
Yeah.
Okay. Well, as I said before, we don't know actually what kind of the method they're using for the explosion. And as far as we know, only we can see the waveform different. 5 nuclear explosions have, especially the first one, this is the first event, has quite different from compare other 4 nuclear explosions. So we can assume that the first event is different, quite different from rest of the nuclear explosions. And the first one has something like start in a vertical cylinder something and a vertically distributed source, and is shaft the explosion. The rest of them maybe we can guess in the horizontal tunnels, but it's not only there's the same line, it's up and down the different level depths in the horizontal tunnels. I think they explode. This means horizontally distributed source, the rest of a nuclear explosion. That's what I guess.
Thanks very much, Dr. Kim. I have a question for Dr. Guillem, actually. What would be your interpretation of the large CLVD component in your moment tensor decomposition?
Not me.
Oh, Dr. Guillem.
I don't really know. That's what I can say. All I know is that I need to fit some non-isotropic component to the waveforms. And it doesn't seem to be satisfied by double couple energy, but just CLVD. So CLVD would be, in this case, dipole, vertical dipole. So in this case, would have some type of explosion type motion that would be constrained on the side and could propagate north, sort of up and down.
Okay, thanks very much. Any other questions, either for Dr. Guillem or Dr. Wei-Jung Kim? One more question here. May we have a microphone on the...
Yeah, thank you for your very nice presentation. If I got it right, you did mention that you made an assumption of the depth, but I've noted that you did a full waveform inversion, is it? So why didn't you not determine the depth from the inversion? Okay, you make an assumption and then you get a final solution for the...
So I didn't show that, but we tried several depths, from 200-meter depths to 3-kilometer depths for the source. And given the waveforms that we are considering and the long period of it, between 15 and 30 seconds, and the distance range we are considering, the wavelength is not short enough to try to constrain very closely the depths. It would be mostly, we get a plateau between 400 meters and about 1 kilometer. That's what we obtain, but we cannot precise the depths. So in this presentation, I'm just showing at 1 kilometer depth to have a standard comparison between all events.
Thanks very much. Any more questions from the audience? Okay. So I suppose we should close the session then. As a reminder, the first part of the session, sorry. As a reminder, if you have a poster preview slide, please check with people on my left here so that you know what order you will be presenting this session. We are a little bit ahead of time, so we may maybe start the second part of the session. And the first speaker for the second part is Dr. Ziolkowski from the University of Edinburgh.
Yeah, thank you, Mr. Chairman. So this is not exactly the title that's in the book. And I'm using the 2009 and 2013 explosions, but I'm actually going to try to get the time signatures of all the events. So first of all, I want to thank the CTBTO for accepting my paper and for supporting me to come to Vienna and give it. And then I also have some other people to thank: David Bowers, Steve Gibbons, Bob Pierce, David Wright, and 3 students, Elizabeth Salter, Nandini Niagara, and Yongcheng Dai, who have worked with me on some of these things. So I want to start by talking about, first of all, what explosions are, yield, and what the source time function is. Then I want to talk about the scaling law for the source time function. And then I want to apply the scaling law to the North Korean events as measured at MDJ in China. And I'd be looking at ratios of spectra, and when you deal with ratios, you can't get absolute amplitudes. So then I'm going to calibrate the source signature I get out of the data against measurements made at Nevada test site. And then after that calibration, I get the source signatures for all 5 events. So first of all, yield. So the conventional estimation of yield, as far as I understand it, is using MB. So MB is a measure of seismic energy released by the earthquake. And so it has to be, yield must be related to MB. So when you look at the relationship, first of all, you've got to get MB. So you measure the amplitude, you measure the period, then there's another factor that depends on the path. So that gives you MB. Then you go from MB to yield, and there are two more constants that you've got to know. So there's a lot of things you have to know about the path between the source and the receiver. And these things are known for Nevada test site and Semipalatinsk test site, but they're not known for North Korea. So there's no consensus about what the yield of these events is. So now, an explosion. So we have explosion. At the center of the explosion, there's a cavity, which is high pressure gas, very high pressure, high temperature. It vaporizes the rock in the vicinity. And then surrounding that cavity is a nonlinear zone where the rock is fractured. And then when you go far enough away, you come to this circle here. It's a sphere, or approximately a sphere, and that's the elastic sphere, and of radius A, the elastic radius, and outside that sphere, the propagation is elastic. So the rock returns to its original state after the wave has gone past. So at the elastic radius, there's a displacement U as a function of A and T, time. And the surface area of that sphere is 4 pi A squared. So there's a volume injected by the source, which is 4 pi A squared times U. And so I call it the injected volume, but if you look in the literature, it's called the reduced displacement potential, which is very mysterious. So anyway, let's just call it the injected volume. So just to give an idea of how big these things are, so for 5 kilotons, given the strains that you get, elastic strains, you have to have A is about 100 meters for 5 kilotons. So to show what they look like, so this is from Sharp's model, that's the displacement, this is the velocity, so the time derivative of that, and there's something wrong with it because it jumps immediately to a value, so that means the acceleration is infinite, so that's not right. So what I do is I just apply a little filter, a low-pass filter, to get rid of that. But those are the kind of numbers that you need to put into the model to get something that has the right period. So most of the energy is contained by the nonlinear zone, and then there is elastic energy that comes out of it. So now, scaling. On the left is the first explosion that we looked at, and on the right is a scaled explosion. And I've scaled everything that you can see by factor alpha. So the radius is alpha times A. The displacement is alpha times U. So the injected volume is 4 pi A squared times alpha squared, and then there's another alpha there, so you get alpha cubed here. So this is called cubic scaling because the volume is obviously proportional to the yield. And so the amplitude, the size of this, the radius is proportional to the cube root of the yield. And this cube root scaling law has been known since the 1950s, at least. So now let's compare S1 and S2. So here's the volume injection for S1. Here's volume injection for, well, I'm calling it S2. Here's the velocity. And I've taken care of this part. And also, I can tell you, that's incorporated in these volumes here because I integrated the velocity to get to the displacement. And then on the right, you have the spectra, amplitude spectra of these two time functions. So let's call them S1 and S2. And the scaling law is here, S2 of t equals alpha squared S1 of t over alpha, and in the frequency domain, S2 of f equals alpha cubed S2 of alpha f. Now, I want to show you that I can recover the wavelets from the seismograms, but I'm going to show you with synthetics. So we start with the Green's function. So here's a nice Green's function in the time domain. And then at the bottom is the amplitude spectrum of that Green's function. Now I convolve the Green's function with two wavelets, S1 and S2. And so I get two seismograms. You can probably hardly see them, but S1 is in black and S2 is in gray. And then we can look at the amplitude spectra, and we have S1 in black and S2 in gray. And you notice that there's more decay on the high frequencies than there is for the Green's function. So the Green's function has a broader bandwidth than the seismograms. So in the frequency domain, we write, in the frequency domain, too many buttons. Those are the two seismograms in the frequency domain, x1 of f, x2 of f. Now let's take the ratio. So that's the ratio, and it's x2 of f divided by x1 of f. And remember that x2 of t and x1 of t are measurements, so x2 of f and x1 of f are data. Then there's no noise in this, in these synthetics. So when we take the ratio of the spectra of the seismograms, that's the same as the ratio of the two source time functions, spectra of the two source time functions. The Green's function has gone away. So now let's introduce the scaling law at the bottom. And then we notice we've got two equations with two unknowns, S2 and S1, and we've got this quantity R, which we obtained from the data. So we've got two equations and two unknowns, which we solve for S1 and S2. So there's the solution. So I got it from those synthetics. Okay, now let's look at real data. So there's North Korea. There's the test site. There are all these Chinese. So this comes from a paper by Zhang and Wen, who did locations of the North Korean events. So I'm giving an excuse on the right-hand side about why I only use MDJ. But okay, so here are the events seen at MDJ, and I've got all these events on the same scale. So 2006, 2009, 13, 16 the first one, 16 the second one. And then on the right-hand side, I have the same events, but I've made them more or less the same amplitude. And what you can see is that they're not identical, and there are differences, and presumably those differences are caused by differences in the source time function and not differences in the Green's function, because they're all very close together, these events. Now, we know that there's no agreement about where these events are. So I've got these locations are from Zhang and Wen. So there's the first one, the second one, the third one, fourth one, the fifth one. These are 1 kilometer squares. Now, this is a geological map of North Korea, or part of the northeast corner of North Korea. And I got this map just down the road from where I work. It was made by the Imperial Geological Survey of Japan in 1926. and it's been translated. So this is granite, this is gneiss, and this is basalt. And this area of 1 kilometer squares is right here in the basalt. So I think these events are in basalt. So now I'm looking at 2009 and 2013, and here are the parts of the seismograms. These are the spectra from the full seismograms. So there's X2 and X1, and X2 is 2013 and X1 is 2009, and there's the ratio. Now, I didn't take the ratio. I said, let's make a filter that shapes X1 of t into X2 of t. Then we don't have to do any ratios. And the filter is short. It's only 1 second long because the source time functions are short. So you can't have a long filter to convert a short thing into a short thing. So we've got a short filter. And then there's the amplitude spectrum of that filter. So I put it into my algorithm to get the source time functions. And this is what I get. So this is the source time function for 2009. That's the scaled version 2013. Here's the injected volume for 2009, 2013. And now there isn't a proper scale on these. And these are the amplitude spectra of these two injected volume rate functions. So now we need to calibrate them. So here are some data from Nevada test site, alluvium, granite, salt, and tuff, published in 1963 by Worth and Herbst in JGR. So we're in a volcanic province. The only ones that are interesting to us are granite and tuff, and the thing we get out doesn't look like either of them. So there's the tuff, and there's the granite. It looks like something in between. So remember that these are in basalt. So I have a geologist friend who has an office just next to me, and I asked him about the basalt in North Korea, and he says, well, it's Mesozoic, and it's been weathered. And basalt weathers very fast, and so after a long time, it becomes clay. So somehow it's not as strong as it was when it was young, and it's weaker than, it's probably stronger than tuff. So I've got absolute time here, and absolute time is here, and the time to the peak of this thing, of extracted wavelet, is less than the time to the peak for the tuff, but greater than the time to the peak for the granite. So what number shall I say for the yield? So I say maybe it's 5 kilotons. And of course, we don't know how good that 5 is. After we do that, we can then say, well, we use the scaling law to get to the source time functions for all the other ones. So what scaling factor do we use? Well, we use the scaling factor that gives us the best answer. You know, we're geophysicists, you know. So we convolve each one of these source time functions with a Green's function. Now, the Green's function I get from the 2009 seismogram by deconvolving for the 2009 source time function that's just been extracted. So here are the seismograms, the synthetics, compared with the measurements. So there's 2009, which is perfect, of course, because I'm just taking that and I'm using my extracted source time function to get the Green's function. Then I convolve the Green's function with something to give me 2006, something else for 2009, another one for 2016, the first one, 2016, the second one. These two matches aren't too bad. The one with 2006 is not very good. But on the whole, the match is pretty good. So the yields that I get out, so these are the scale factors that give me those matches. Here are the yields, 1, 5, 12, 8.9, and 16.2. And it all depends on that 5. and that's uncertain. I don't know what is 5 plus or minus something, but I think the scale factors are good. So I think the ratios are more precise than the absolute values. So I have managed to get the source signatures for all the events directly from seismograms from one station. And I think they show that the scaling law is approximately correct. The yield ratios are better than the absolute values. And the Green's function, as we noted, has higher resolution than the seismograms. So if you can get at the source time function, you can always improve the resolution of the data. And once you've got, once you've got the source time, once you've got the Green's function, then you can use it for other events, as we've shown here. And once you've got the source time functions, you can then use that for other stations to get the Green's functions. Right? Thank you for your attention.
Thank you very much. We have time for a few questions. Over there.
In your yield estimation, I wonder if you had any chance to think about depth effect.
Well, yeah, I've asked so I know that, for example, Miller and Murphy, they say that depth is very important. And in their model, they say the depth is really critical, and they also say the Green's function is the same for two different events. Now, you can't have it both ways. So the events are not in the same place, so the Green's function can't be identical. So I think there's an approximation there, and the depth obviously comes into it, and there is an error because the depths are not the same. But you know, I think that error is the same error as the error in the Green's function. So we're expecting it to divide out. It won't divide out. There are probably bigger problems than the depth. I mean, we know that the size of the elastic zone is on the order of 100 meters. I don't believe that any of these places are isotropic over 100 meters. So I think there's an anisotropy is probably a bigger effect than depth maybe. Yeah.
We'll take one more question and then we'll go to the next talk.
Okay. Thank you for your excellent talk. I just want to repeat the question from Professor Richards. What do you think about the application of your method to the events with known depth and closer measurements of Green function? Does it work for them?
Well, I have only applied it to these events. Actually, I think this will work. I should thank you, Ivan, first of all, for your comment. Thank you. But I think this will also work for earthquakes. So I would like to try this for earthquakes because I think the only difference between earthquakes and explosions is really there's a factor. So with the earthquake, you have the moment, source moment, and that's equal to volume times the shear modulus. And that's just a factor. So I think the scaling law will apply to earthquakes. And so I would like to try this on earthquakes and where depths are known, you know. Right.
Thank you very much, Dr. Ziolkowski. The next talk is by Jelle Assink from the Royal Netherlands Meteorological Institute.
Thank you. Good afternoon. My name is Jelle Assink. Indeed, I work at the Royal Netherlands Meteorological Institute. We are the Dutch National Data Center for the verification of the CTBT. Today, I would like to discuss the combined use of seismic and acoustic data and the use for the estimation of source depth. And we apply this method to the recent nuclear underground tests in North Korea. And this is a work that I present on behalf of my co-authors, Gil Averboeg, Pieter Smets, and Laszlo Evers, all from the Netherlands. So this plot has been shown before by many presenters today. Indeed, North Korea has tested several tests, 5 within the time frame of about 10 years. These tests are well picked up by the seismic network worldwide. So this figure shows the nearby station NDJ in China, and it shows very nicely that the tests are getting larger with time. Today I will discuss in more detail the third and the fourth test that had about a similar magnitude. But the point that I want to make today is that while the epicenter estimation and the origin time and yield are well to estimate using the seismic network, the depth is typically a little bit more difficult. And the idea is that the use of acoustic data can help there. So this is just a frame that shows the seismic waveform as a function of distance. So I've plotted one of the underground nuclear explosions from North Korea, and you see the P wave propagating over the over distance. And so basically, of course, as we all know, with the seismic network, we can well estimate where the source is located, what the origin time is, and what the yield is. And this is, for example, shown here by this analysis by NORSAR, where they have attached TNT equivalent numbers to the different tests. So, and as I mentioned before, I will focus on the January 2016 and the February 2013 tests that had an estimated yield of about 10 kilotons of TNT, although I have to say that the January test was estimated to be a little bit smaller. So besides detection on the seismic network, there was also a detection of infrasound on the IMS infrasound arrays in the vicinity. And those stations are shown here on the map, as you can see here. So this is the region of Southeast Asia, of course, the North Korean test site. So there's an infrasound station at about 400 kilometers distance, IS-45. It has 4 microbarometer arrays, 4 microbarometers, as you can see here. And there's also a station in Japan, IS-30, that is at about 1,187 kilometers distance. This one has 6 elements. So the 2013 test was well detected at both stations. The 2016 January test was only detected at IS-45, whereas they had about a similar yield estimate, as I already indicated. So that's somewhat interesting, because what would be the difference between these two? Of course, you could think about the difference in the atmospheric state, which infrasound is very sensitive to. So these are all matters that we want to take into account in our study. So this is a somewhat complicated slide that shows results from the array processing. The basic message is basically that what you see here is are the array processing results from IS-45. So on the left are the results from 2013, the right shows the results from 2016, and you see the relevant detection shown here in red. Now, the take-home message is that the 2016 detections were much weaker compared to the 2013 detections, which are shown here in red indeed. So you see 3 relevant detections. So the relevance is based on the array processing parameters, of course. So you see here, as a function of time, the different parameters, the apparent velocity, the back azimuth, the signal-to-noise ratio, the best beam, and the spectrogram. So all are determined from the array processing results. So you can see here that there's 3 clear arrivals. There's 1 weaker arrival here. So the arrivals are spaced in time. This has to do with the propagation through the different waveguides of the atmosphere that I will come to later. And you can also see that the colors in the spectrogram are also different. So it seems a little bit more red here in 2016 compared to 2013. And it has to do with the fact that the surface wind level was much higher in 2016, and that has implications for the noise level. And of course, higher surface winds means that it's more difficult to detect. So the last aspect that I want to discuss on this slide are the blue dots that are also shown here. I hope you can see them in the back. So these are the estimated parameters that we get from ray tracing. So we have taken an atmosphere and propagated rays through there from the nuclear test sites towards IS-45. And what is interesting to see is that the blue dots agree quite well with the red dots. So that means that we can explain our observations at IS-45 rather well. So what do we have now? There's the seismic signals that are coming from the underground nuclear tests. So the idea is that if you put it down in a cartoon, is that they propagate into the solid earth, of course, and they reach stations like MDJ that I showed on the first slide. But the seismic energy will also couple to the atmosphere. So you basically have to think of a concept that the seismic energy will propagate up to the Earth's surface. The Earth's surface will start to shake as if it is a giant loudspeaker, and that will start to generate infrasounds. And you can see that here with this nice figure on the left-hand side, where infrasound is generated above this mountaintop. So then, of course, the seismic energy will propagate to a seismic station, whereas the atmospheric infrasound will propagate through an infrasound station, say IS-45. So the idea is that the deeper you go with your seismic source, the less coupling there is between the underground and the atmosphere. And this is something interesting, as it could imply that we could use these observations from 2013 February and 2016 January to say something about the source depth. As I already indicated, this is difficult to estimate from teleseismic data. Of course, we have to take the state of the atmosphere into account and the surface winds to estimate the noise levels and such. So this is all done. So for the propagation, I'll get to that in the next slide. So this shows infrasound propagation in the atmosphere. We have computed a full wave and a ray tracing solution for the 2013 February and 2016 cases. So we took ECMWF data, the European Center for Medium Range Weather Forecasts. They provide analyses, basically provides you the state of the atmosphere, gives you information of temperature and wind as a function of altitude. And this information is then used to get an idea of what the infrasound propagation is in terms of propagation losses and propagation paths. So you see somewhat a red band here and a red band here going up and down. So this is infrasound propagating in the, both tropospheric and stratospheric waveguides. And you see a similar situation, somewhat different in 2016. And it is somewhat changed, and it has to do with the fact that the atmosphere, of course, has changed. And I will come back to 2016 a little bit later, because there's also a special case at hand at that particular time. What is important from this slide also to notice is there's a difference in propagation efficiency. So basically, if you look at the different propagation paths, and in particular the stratospheric paths, and if you look at the numbers more closely, you can see that there's a difference in propagation efficiency of about 5 decimals. And this is something that we will use in our source depth estimates later. So what about the state of the atmosphere that I mentioned? So for that, I took atmospheric specifications at about 45 kilometers altitude. So that corresponds to a level of about 1 hectopascal. And what you see here are the specifications of temperature and wind for the 2013 on the left and 2016 on the right-hand side. So on the left-hand side, so this is the temperature for the northern hemisphere. The test site is shown here with the arrays IS-45 and IS-30. So the 2013 case is a typical winter atmosphere where you have a cold Arctic pole with an associated eastward circumpolar vortex, which is very beneficial for eastward propagation. So propagation from the test site towards IS-45 and IS-30. However, in January 2016, you can see that there's somewhat of a temperature perturbation at this altitude. And also let me mention that this altitude is important as it signifies the top of the stratospheric waveguide, so it is in that sense very important. So the temperature has increased a lot, and this is something that we refer to as a sudden stratospheric warming. It has to do with the fact that planetary waves may propagate upward during the winter, and they may deposit energy in the stratosphere, and that leads to this increase of temperature. And there's an associated change in the winds as well. So this classical eastward circumpolar vortex that you see here is somewhat displaced towards the pole, and westward wind is starting to flow, and that in fact inhibits propagation from the test site towards IS-30. So you can see that the state of the atmosphere is rather important for in the consideration of infrasound detection. So we took this all together, and we came up with somewhat of a preliminary estimate of the relative depth of the source by taking into account the difference in propagation efficiency and the observed pressures at the station in Russia. So that's shown by this equation here. If you want more details, you can read our GRL paper that was released last year. So basically, if you plug in all these, the numbers from the study, we found that the 2016 test may have happened at about a depth of 1.5 times deeper than the 2013 test. And if you want to apply some, or get a feel for absolute numbers, you can assume, based on this 10 kiloton TNT estimate for this test, that the minimum source depth must have been about 450 meters, and then for the 2016 January case, it must have been 225 meters deeper. That is 675 meters. So something that I just want to touch on briefly is some new work that is going on in our institutes. We are working now on a coupled seismoacoustic model where we combine both the solid Earth and underneath an atmosphere to quantify the effects of coupling. So these two cases show the propagation for 2013 and 2016, and so from this we estimate that the difference in infrasound propagation, taking into account the different source depths, is about 15 decibel, and that's an order of magnitude in agreement with our observations. So with that, I would like to summarize. So in our observations, we have seen that the underground tests also produce observable infrasound besides seismic energy. The infrasound detections were observed on IMS infrasound arrays in Japan and in Russia. In January 2016, only a weak detection was observed in Russia, and we could, as I showed on the array processing slides, well explain these detections with infrasound propagation modeling. And then using this infrasound propagation modeling and a simplified estimate, so this makes some simplifying assumptions, such as the assumption that the yield is similar, the geological conditions are similar. So based on all these assumptions, we come up with a preliminary estimate that the 2016 January test occurred at about 1.5 times deeper than the 2013 test. And in such a case, less infrasonic energy will couple to the atmosphere. So basically, this is a case that I think clearly shows the synergy between seismic and acoustics, and we hope to further explore these cases. It's, I think, very interesting, and there's, of course, more complexities that we're hoping to explore in the near future. Thank you.
Thank you very much, Dr. Assink, for a very interesting talk. I see that we have one question already from the audience.
I wonder if you applied wind correction to the amplitude of infrasound.
Well, anyway, it's not important. So the wind is taken into, you mean the surface winds or the stratospheric winds, for example? Yeah, so the stratospheric winds are taken into account in the infrasound propagation modeling. So basically you get a transfer function for the propagation from the source to the receiver, and that gives you information about the effect of the winds on propagation. So we could clearly see that in 2013 the winds were much stronger in the direction of propagation, and that that led to more efficient propagation conditions by about 5 decibels.
Thank you. Any other questions of Dr. Assink?
what sort of uncertainty bounds do you put on your factor of 1.5, and how did you obtain them?
Well, we haven't quite gone so far yet. That's a very good question. So I think to do this in the right way, you really want to capture all the uncertainties that are in the atmospheric model as well. I had actually prepared a slide that also shows the uncertainties in so these effective sound speed profiles that are important for propagation modeling. So you also want to take into account the geological conditions, the uncertainties in the yields. So this is something that we're basically working on, and it's very important.
One more question.
To my understanding, your estimation of about the relative depths strongly depends on the precision of the propagation difference for the two events. My question is, your modeling, your numerical modeling is precise enough to support this estimation. And the second, you mentioned that the January 2016 Korean nuclear test generate weaker infrasound signals than 2013. But I may remind you, in other directions, the 2016 event generate quite large, much larger infrasound than the 2013. We have that data.
Well, so I suppose you mean the South Korean infrasound arrays. So I haven't had a chance to look at those. Of course, all these findings are based on just the observations at two infrasound arrays at a rather far distance. So I would love to get my hands on some additional data to get a further estimate on the uncertainties and the likelihood of her findings. But I think the point is that independent of what we find in terms of data, it's still a very useful technique to combine both seismic and acoustic data together. As we all know, seismic recorders are not very sparse in the neighborhood of the Korean test site. So, please send me the South Korean data, and then we can do some more analysis.
Okay, one more question from.
Well, I think the 2013 event at IS-45 is also characterized that you have a range of detections, because I think I've seen in your slide at least 3 separate points. So I guess you have assumed and came up with this factor of 1.5 scaling to the last peak, which was the biggest peak. Mm-hmm. I mean, have you looked into the possibility that other peaks should have been considered and looked at those ratios?
That is a good question. Actually, I did at some point. Dr. Alexis Lepichon emailed me with the same question, and so I did it for the tropospheric arrivals, and then I found that the 2016 detection would have happened at about a depth of about 10 kilometers. So I would have estimated that the North Koreans hadn't gone so far to dig 10 kilometers. So that's the reason why we went for the stratospheric arrival.
Okay. If there are no more questions, we'll go to the poster preview slides now. So if the presenters are ready to present their slides, would they please get ready to line up and make their presentations?
Important thing discussed today is the magnitude difference between 5 DPRK cases. It's almost 1 year from the last event, and we present the method which is based on cross-correlation comparison between waveforms at IMS stations, which shows that us very accurate difference even for one station, as we also just saw from the professor talk. Okay, thank you. And the next one. And this is about absolute relative location of IDC. By IDC, the 5 DPRK events. This poster presents the IDC interactive locations and compares it with the relative locations based on waveframe cross-correlation. We show the peer-wise comparison, all pairs of 5 DPRK events, and also the joint inversion for the relative location of all 5 events altogether. Thank you.
At German NDC, we perform automatic forecasts for the atmospheric dispersion from the DPRK test sites 4 times a day since 2012. And on the poster, there is a statistical analysis, especially for seasonal patterns of those more than 6,000 dispersion runs. And one result is that we need the USRK station in the northern summer because in July there's nearly no sensitivity to Takasaki. And another thing that is on the poster is high resolution backward atmospheric transport modeling for the Xenon 133 peaks in February 2016, which are compared with the source region of the 133 Xenon peaks, which were observed in 2015 in background at Takasaki.
Good afternoon. This poster will present the technique that we are using at CTBTO to monitor the situation after the nuclear test of DPRK. 2 tests in 2016 are considered, so we demonstrate as well impact of seasonal trends in the wind field spatial distribution. And also we reveal what kind of techniques are used when there is an event but nothing is detected at the station, and what kind of technique we are using if the station will detect an elevated value of radionuclide substance. So I would encourage you to visit our poster. Thank you.
Good afternoon. This poster describes the results from the source physics experiment, which is a series of chemical explosions done at the former Nevada test site to better understand how explosions generate seismic waves. We've completed the first phase, which was a series of 6 explosions, chemical explosions done at a range of different depths and sizes and recorded on the same network. And in particular, for the 5th and largest shot, we were able to deploy a very dense network of 1,000 stations, which are shown here, so we could see in detail how P waves and surface waves are being converted to shear waves through propagation. So if you're interested in looking at that and understanding some of the questions about depth scaling that we've been talking about in this session, please come by the poster. Thank you.
About 50 days after the DPRK 2013 test, radioxenon was detected and associated with the test at Takasaki and USRK. So the question was, after the 2 tests of 2016, whether such a thing would happen again. And all detections of radioxenon were scrutinized with atmospheric transport modeling, whether they are possibly consistent with the assumption they are coming from the DPRK test site. And for those episodes that were selected based on ATM, we more tried to look into isotopic ratios, but unfortunately only xenon 33 was measured, and so we were chasing for 131M by reducing the MDC with a summing technique. There is another poster on that, and with laboratory analysis. So the result on that you see on our poster. It's a teamwork of the IMS and IDC divisions. Thank you very much.
As introduced by Martin in the previous poster, this is one of the techniques that we developed at the IDC within the spatial analysis after DPRK 2016. And the idea was to combine spectral data from the IMS stations and then to improve the detection sensitivity and also the uncertainty on the results. This has been successfully tested on both noble gas and particulate spectra from the Takasaki station in Japan. Thank you.
Good day. On 8 September 2016, seismic station of the world, the recording seismic source from the territory of North Korea. This source recorded seismic station of Ukrainian National Data Center. Ukrainian National Data Center is composed of 10 seismic stations located on the territory of Ukraine, Station Akademia Vernadsky on Antarctica, and seismic array, which the primary seismic station PS45 AKSG. Thank you very much.
Thank you very much. I believe that was the last preview presentation. With this, I'd like to thank again our speakers for the session and both the oral presentation and the poster previews. There will be a further 6 oral presentations tomorrow starting at 9 o'clock in this room. So thank you very much, and I thank also the audience for their questions. And of course, we do have a poster session that we strongly encourage you to attend.
1, 2. Yes. So welcome to our demonstration on the radionuclide analysis. My name is Robert Wertze. I'm in the IDC as a radionuclide performance monitoring. And we have here two of our colleagues, two analysts, Franziska Klingberg and Ari Lepanen, sorry. And they will then present the actual work the analysts do when they go through the different spectra. Can we show the first one? For those who are not so familiar with the radionuclide data, in our pipeline, in the IDC pipeline, of course, we get first, in a hypothetical event, we get first the waveform data, and due to the different propagation speed in for the signals, radionuclide data, the actual radionuclides need to reach a station first. Then samples get created, so usually 24 hours of sampling. Then we have some decay process to reduce the background in the samples, and then we measure the sample on a spectrometer. So for the particulate network, between start of sampling to the end of the measurement is usually 72 hours. And for the noble gas, it's 48 hours because there the internal decay is not needed to be so long. So you see here on this scale, so within 1 hour of an event, you would see already the first seismic reports. And then a couple of days later, the first radionuclide data would come into the pipeline, and the automatic radionuclide report will be generated. And that's already then available to the NDCs. And that's actually where then the work of our colleagues, of our analysts come in. It's this step between the automatic radionuclide report and the reviewed radionuclide report. That's the important work of the analysts. They review the results of the automatic software to make sure that all the reported nuclides and all the peaks are identified correctly. And with that, I will hand over to Franziska, who will show you then the first spectra.
Thank you, Robert. So here you can see our so-called web flow. This is basically the first thing that we open in the morning to see how many samples arrived. So each of these here on the left, you can see all the different station names. On top, you can see the date. And then each little green box or colored box represents one spectrum or one sample. You can see here those ones represent, for example, a particulate sample from the AUP06 station, which is already reviewed. So you can see further down the outer category and the category are both 1, so nothing else turned up during the review. And here you have one which has not been reviewed yet, so it only has an outer category. And like this, we can get a quick overview of which spectra, for example, need immediate attention because there is a potential level 5. Such as here. Most of the time it turns out that it's not actually a level 5, but it's a misidentification. So level 5 means that there's 2 anthropogenic isotopes from the list of CTBT relevant isotopes, of which at least one is a fission isotope. So then we go through the spectra and analyze and see if it's actually a level 5 or not. The smaller boxes that you can see here are representative of the SONA system, which has a 12-hour sampling and 12-hour acquisition. So per day, we actually receive 2 spectra which have to be reviewed. And you basically have the same thing. We can look at the different color code. This is, again, a level 1, category 1. And here, for example, and in noble gas, that would translate to a level A. So there we have level A, B, and C instead of level 1 through 5. And here we would have a level B, meaning that there's xenon detection in this sample, but it's normal for the station. So it's not anything of concern to CTBT. Then we can go over to the, I will just switch back to this workflow here for you so that you can have this and keep it in mind. And then here on the other side, we're going to start looking at a spectrum. So I already loaded a spectrum here from a station with collection stop, and I will now try to talk you through each of the steps that we go through during the analysis. So we can just start by looking at the peak info. And if there's a small lag, I apologize, but it's due to the network connection that we have here. So we can see collection start, collection stop. And I hope you can follow, but I think it's best if you try to follow my mouse pointer, as I can't use a laser pointer from here. Then we have a sampling time of 24 hours, a decay time of 24 hours, and then the acquisition, as well as the submitting time from the station and when it was received in IDC and went through automatic processing. We have the same kind of state of health qualifiers up here, and these will appear in red. So we have the flow rate here, which has to be above 500 cubic meter per hour on average. So if this is lower, it would turn red. And the same for the sampling time, decay time, acquisition time, and reporting time. And here, there you see two, so it means we have the one when it was sent and the time when it was received. So if any of those doesn't fulfill our SOH requirements, they will turn red and give the analyst an indicator to follow up, for example, with our ops section to see what went wrong at the station. Then additionally, up here we have QC flags. For the calibration, we always check the beryllium 7 and the potassium 40 peak, which are naturally occurring, and you can see that the energy calibration is within our requirements of 0.8 keV. So the black one is the actual energy it should be, and then the peak location in energy. You can see the spectrum is assigned to me, and you have all sorts of other things. For example, if I'm unsure if this is a normal spectrum for the station, I could compare it to the MRP, which you see down here, meaning most recent prior, and I compare it, so meaning the spectrum from the day before. And I can compare it, oh, I'm sorry. So there you go. So you see it has a similar shape as the day before, so I'm suspecting that nothing went wrong and it's really normal for the station. Then here we have a peak search list. So all the peaks which were identified in the spectrum have been automatically identified, except two peaks, which you can see here. They're uncommented peaks. So for level 1, which you can see the category here, you can click on it, and it tells you the activity and the level which it has to for example, the beryllium activity has to exceed 3,700 microbecquerel per cubic meter to turn into a level B, so abnormal concentration for the station. We could also just go to the peak and check it out, have a look at the peak shape if everything is fine. We can even go in the nuclide review and see it is also suggesting me iridium 190, but of course here the key line is actually not there. So the gray area is if this peak, the 477, would all be attributed to iridium 190, we would expect a peak of this height at 168 kV. So this is not the case, so I know it's beryllium, which fits much better, but also has no secondary lines. Then I can either go through the list here, or I can just directly go to the unknown peaks. This is just a baseline issue in the automatic processing. So I'm going to call this a false peak since it's not really a peak and cannot be associated with anything. And here we have a peak, and it's not it doesn't have a nuclide ID associated with it, and it's not suggesting me anything. So what I can do is I can go into the nuclide review. Oh, and I'm sorry, I'll apologize. I will also show you the SCAC. So
The yellow line is the spectrum, the white means it's an unidentified peak, and I can also click here on SCAC, which shows me a smoothened curve to better indicate me where the peak is, which is sometimes very helpful if you have peaks with low count rates. Sometimes you can't really decide is it a peak or not. And then the red line is indicating the LC, so the critical limit, which is helping me to decide whether this is considered a peak or not in a statistical sense. So then I can go in the nuclide review. I see here the energy. Since it can't find any identification, I can increase the tolerance, and it's suggesting me lead-212 family, which is basically all the radon decay products. And it's also suggesting me bismuth. But you can see here the energy doesn't fit as well as for the lead-212. And additionally, the key line, which is at a 609 kV, which you can tell by the combination of abundance and efficiency, gives us the DPI. So the higher the DPI, the more likely it is to detect. So here you don't see any peak at the key line, so it can't be bismuth 214. So I'm going to call it lead-212, which I can do either by trying to see if it's suggesting it to me if I kind of shift the centroid over a bit. So it's taking a while. Okay. And then we could also just go through the spectrum to see if there's any missed peaks. Usually missed peaks occur mostly if there is a multiplet which hasn't been resolved properly. So as an analyst, I would just go through each of these peaks and see if there's anything nearby which has been missed. So any peak which is above the LC but has not been identified, and then I would insert it. Here we have some more quality flags on top. You can click them. One of them is that we like to have the resolution for the beryllium peak, so the peak at 477.6 keV to be below 1.7. In this case, it is 1.2, so that is fine. Another important indicator is the barium NDC, which is one of our quality control checks. It has to be below 30 microbecquerel per cubic meter. This is fulfilled as well. And then, of course, we are very happy if most of the peaks are automatically identified, and this will turn red if, I think, if only 80% are identified, which can also be an indicator. For example, if we have a gain shift during spectrum acquisition, which result in double peaks, then of course we have a lot of unknown peaks. And then once I'm done, so once I checked all the peaks and missing peaks, we can release the spectrum, which would then create a RRR, a reviewed radionuclide report, which can be seen on the secure web portal website, and I think can also be requested through mail products and so forth. Here's another small check. We can see the activity, the upper limit. It should be level 1. It is. We can preview the RRR. So this is the product that the member states will get. We have all this information, the time delay between the sample or the spectrum arrival rather and the creation of the RRR. And we have collection start, stop. Again, all the flags that we already checked. We will have the peak search report here, and then you can see little comments here. And those are the ones which either the analyst inserted or found later. So here I named one of the peaks lead-212, which is comment 3, which was this peak at 1511 keV. So then I can have a look. Everything is fine. I'm happy. I can release the spectrum and the product will be created. So this is a level 1 sample, so it's really rather boring because it has very low activity due to its location on an island. We can also have stations with a lot more background, and I'm just going to show you an overlay. from a station, from a Russian station, and you can see here the natural background. So this, the white spectrum, is the one which I'm just comparing it to. Now is from RUP 58 station, so you can see that there's a lot more natural background. It's still a level 1, but just due to the higher radon content in that area, we have much more peaks and much higher overall activity in the spectrum. Then, since it's a bit more interesting, I will also show you a level 4, which we recently had in Chile, CLP19. And here I already commented all the uncommented peaks, which are mainly natural radioactivity. And then here now you see, which you didn't have in the other one, here you don't see any red box on the right screen. Here I see, 3 anthropogenic peaks. I have to check those, of course, before releasing the spectrum. And it is iodine 131. I'm going to the key line, which is this one. And I can have a look also in the radionuclide review, just to see that it is actually iodine 131. This is a very clear case. We have 3 peaks from the isotope clearly identified at the good energy, and the fitted area fits perfectly with the actual measurement. And so in this case, I would confirm the ID, and then once I confirmed all 3 of them, and of course checked all the other things which I've just showed you with level 1 spectrum, you can also preview the RRR, which is taking a bit longer. Well, anyway, then you will again see the list of ISO. You will have the same as for the category 1 spectrum, but you will have a confirmed iodine detection, so it will be released as a category 4 spectrum, which usually you can see here. I'm sorry, I can't hear due to the, maybe, Robert, I don't know.
Yeah, does the RRR have the energy calibration that was used by the analyst?
I'm sorry, I can't understand with the echo, so if maybe Robert can just, I don't know. I'm sorry.
Does the RRR have the energy calibration that the analyst used?
I believe so.
Oh, okay.
So if you scroll all the way to the end, so here you have the peak search results, the activities found, the comments on all the peaks, and then here you have your energy, and this is the calibration which has been used. So you could extract that, if you get them in text format, you could extract that and then use the same parameters as the IDC did. Are there any more questions? I forgot to ask before, but yeah, are there any more questions? Then I'm going to show you one more spectrum, which was taken just after the Fukushima accident, just to show you a range. So we had a level 1 or several level 1 spectra. And now you had a level 4, so I just wanted to show you a bit the range of things that we see. Of course, Fukushima is an extreme case, and here the spectrum. So here you have 50. Here you can see there were 51 anthropogenic peaks which had to be confirmed, and We can even choose here, we can choose to only show the CTBT relevant, and you can see that it's mainly your iodine, lanthanum, cesiums, and tellurium. Robert, did you want to add anything to this, or? Okay, so this is it for the particulate analysis. If there are no more questions, I will move on to the radioxenon analysis, where we have two technologies, one based on high purity germanium and the other one based on beta gamma analysis. So I preloaded the spectrum. And I chose the level C just because it is more interesting. You can already see that the way this works is the SPELAC system is sampling for 24 hours and then is processing the gas, so it's extracting the radioxenon and then inserting it for measurement into the detector. And we are looking namely for the 4 xenon isotopes, xenon 133, 133M, 131M, and 135. So this view is much more simplified since we really don't care much about any other isotopes in this other than for calibration. The setup is the same. We have here our state of health and quality control flags. We have the xenon MDC, which is required to be 1 millibecquerel per cubic meter or less, so it's green because it's 0.3. The xenon volume has to be more than 0.8 milliliter, which is also fine. The sampling time is 24 hours. Acquisition time is, in this case, 22 hours, and the reporting time is the sum of those plus the processing. The QC flags up here don't apply. It's just the same ones, so the GUI just didn't change this. So disregard this. You just want everything here to be green, then you're happy. You can do the same. You can compare the spectrum with the previous spectrum. So it looks very similar, except for single peaks, which we will see afterwards. And we can also actually look at preliminary spectra, which I forgot to mention in the particulates. So we can look at preliminary spectra which come every 2 hours, which is good if we have an anthropogenic isotope which has a short half-life, so that we can see its development over time. This is less important in this case. So for the xenon, we have the big button here, xenon review. If you want to compare that, we didn't have that here in the particulate. So you see all this kind of went away and was replaced by the xenon review. Which is loading. So in this window, you can see the X-ray region from 28 to 36 keV. The pink and red lines are indicating where we are expecting the X-rays. At 250 keV, if there is any, we would expect xenon 135, and we can see here that there is actually a detection. The 131 M is at 164 keV. There's nothing obvious here. Xenon 133M, there could be a little bit, but as we can see, it is below the critical limit. So it's not considered a real peak. And then here we can see the xenon 133 at 81 keV, which also is a good peak. And again, we have the yellow curve, which is the actual measurement compared to a Gauss fit. So now I still have to make sure that the spectrum is calibrated correctly, and I do that by, so all the SPELAC spectra have either a lead-210 line or an americium-241 line. So I'm just going to do this manually here, insert the energy, and say go to, so he's going to the energy. You can see there's barely any lead-210. So let's try americium-241. So here's the peak. We can see the energy is fine, and then the other end would be a lead 214 peak at 253 kV, which is fine. And we can also additionally check a line which is close to the 81 kV line at 77 kV. So I would say that the energy calibration of this spectrum is good. So I don't have to recalibrate it. Then I would also additionally check, because sometimes we have baseline problems, additionally check if the peaks are actually here in the X-ray region, and you can clearly see them, the ones which we had in the xenon review earlier. So these correspond to these ones, and then the same for xenon 133. And here for xenon 131M at 164 kV, it's really just to ensure that the automatic algorithm didn't miss anything. And so we just go through the whole spectrum and make sure that the automatic processing didn't miss anything. So with this one, I would call it a day, and the categorization, of course, comes from the fact that this is a detection of xenon 133 and 135, which is above the abnormal limit for the station. Please disregard this one here. This is just saying 0 because we are in our testing environment and not our operational environment. So here I would release, unfortunately here I cannot preview the RRR, but I have the sample release window, and SnT is adding this comment for me saying this sample is categorized as level C due to the detection of 133 and 135. And then, as in the other RRR, you would also be able to see all the findings and the SOH data in the RRR. Are there any questions for this? So now let's move on to the sauna system. For the sauna, we have a different software which is called Norphi, and this is due to the fact that this is a beta gamma coincidence system. So we have 12 hours of sampling, then gas processing, and 12 hours of sample acquisition, so spectrum acquisition. And then after the 12 hours of spectrum acquisition, what we get here is on your y-axis, you see the gamma energy ranging from 0 to 700 kV. And on the x-axis, you can see the beta energy. And each of those dots represents a count which has occurred in coincidence, meaning if there was a beta directly followed by a gamma emission, or even a conversion electron followed by an X-ray, we can see it here. In addition, you can see these boxes here, which we call ROI, regions of interest, and we have different ROIs for the different isotopes. This one actually is our radon ROI, so this is just to check that we didn't get any cross-contamination from the radon during the gas process, because sometimes it can happen that radon also enters the cell, which then will actually interfere with all of these other RIs. This one is the one for xenon 135 at 250 kV in the gamma energy. This one is the one for xenon 133 at 81, centered around 81 kV. And down here you have the X-ray region. And you can see additional boxes, so one which is around 129 kV, which is the conversion electron for xenon 131M, and the one around 199 kV, which is around the conversion electron of xenon 133M. And as you notice, those boxes are not centered around those energies, and that is intentional. Because you want to leave a gap in between here in case you have an overlap of both conversion electrons, so that you don't get too much counts of either isotope into the other RI. Then here on the right-hand side, you can see a spectrum. It's written original gamma, which is the gamma spectrum, the pure gamma spectrum without any coincidences, and I can change it to projected, which means these are only the gammas in coincidence with any beta. And the same down here for beta. So you have the beta energy in the original and then the projected. So only the betas in coincidence with a gamma. Now, as for the SnT software, up here we have a lot of little green buttons, which is again our check of quality, control flags, and SOH. The collection time, 12 hours, which you can also see down here. The acquisition time of 12 hours, which you can also see down here. The xenon volume, which is also fulfilled because it's above 0.87 milliliters. The MDC, and we can click these little boxes just to see the history of the station. So depending on the activity in the sample and whatever else happened, the MDC can vary. So here you just have an overview to see that you have no outliers. And here it tells you that the gas background was acquired and there is an existing detector background. And some more sample volume airflow. So all of these have to fulfill our requirements. Then here you can see a quick overview of the sample information. It's status P means processed, not reviewed yet, and then category A because there's no radioxenon detection in the spectrum. Then here you have a sample, gas background, detector background, and QC. I will go through each one of them. So the sample is the actual sample. Then for the sonar system, before each sample, a gas background is taken in case there's any memory effect of a previous sample, which could then give, let me rephrase, which can happen if we have a high activity concentration sample in the cell. The radioactive xenon can actually seep into the plastic and cause a so-called memory effect in the plastic, which we would see even after flushing out the cell and introducing a new sample into it. So the gas background is taken to make sure that we take into account if there's any xenon seeped into the plastic. Then we have the detector background, which is a 3-day acquisition just taken before, taken during the installation of the station. And then we have the QC spectrum, which is rather important. So the QC for the beta gamma consists actually of point sources because we don't want to put a QC into the gas cell every time. So the QC is entered close to the beta cell, and what you can see here it is, so this is the gamma spectrum in original, which is, this is the cesium 137 peak at 661.7 keV. So we can check the excuse me, you can check the energy calibration here. You can also zoom in, and you can see that there's a bit of a tail on the right-hand side. So this is a thing we should keep an eye on. If this gets worse, we have to inform ops and in the end the station. Then here we have a European peak at 123 keV and at 43 keV, as well as the cesium X-ray at 32. So this calibration looks good to me. And then here what we have is what we call the cesium banana in the coincidence. So it is assumed that the whole energy of the cesium is deposited in the beta gamma system. So the whole Compton, so here you have the photo peak, and then you have the whole Compton ridge going up to the backscatter peak at 185 keV is actually what you can see here. So we can use this knowing that the full deposited energy is 662 keV. So if now I go, for example, to 200 keV in the gamma, I expect the centroid of this to be at 461 keV to have the full energy deposited. And so I can calibrate the beta detector, or recalibrate if necessary, by going through the spectrum and checking several points on this so-called banana to see if the calibration is fine. Are there any questions for this? No. So level A is pretty boring, so I also prepared a level C spectrum. So I can select samples either by sample ID, I'm sorry I did not mention this, or directly just by the site code. So it would be, for example, for the one I chose now, the Swedish station, it would just be SEX63. I can also choose the detector or leave it as a star, so I would get spectra from both detectors. And I can I can choose a collection start or stop range. So here I selected this one for the demonstration. Which is just taking a little time to load. You can ask questions in the meantime. Okay, there we go. So again, it's the same procedure, but this time we can see there is actually something in here which is interesting, and it turned out that this was due to a fuel leakage at a reactor in the vicinity of the station. So it is actually very rare that we can see xenon 135, which is in this second RI here. I will deselect them all. So here is just the RI for xenon 135, around 250 keV. And then basically, and here is the xenon 133 at 81 keV, which you can see really nicely, and of course the according X-rays. So here we would do the same. We check, is there anything in the gas background? You could see that there were some detections a bit previously. There are still some detections in the gas background in the X-ray area. So this would be subtracted automatically by the algorithm in the activity calculation. And we also have to make sure that the spectrum is calibrated correctly, which I did beforehand. So let's just go back to the spectrum. We have the full gamma spectrum here, which in this case doesn't tell us too much, but then if we go to the projected, so again, this is only the gammas which are in coincidence with the beta that we can see here at 81 keV. You can see it very nicely. It fits pretty well, and you can see it also here zoomed in. So this is a bit of a more interesting case, and we had several detections like this. Oh, and I'm going to show you the xenon 135, because here you can't really see it. Unfortunately, this is in linear scale, and I cannot switch it to log scale. So I'm just going to zoom in here. And you can see this. You don't see it so well, but there is a peak here at 250 keV, which I find you can actually see better in the coincidence spectrum itself. So it would be in this area here. So just this area, you can see that there's more counts than in the previous spectrum. So you can see this is an actual real xenon 135 detection, which due to its short half-life of only 9.1 hours is rather rare. But the reactor is really close to the station, so we could see a clear xenon 135 detections. That's it from my side. If there are no more questions, then we would go for a break.
Any questions? Don't be shy. We have the experts here. If not, then thank you very much. We'll have a short break, and then we actually will go through the same thing again for the ones that want to see it again. Thank you very much. Do we have any newcomers that you want to see? I mean,
Off.